Hello everyone, this is Dr. Smita A Patil from P.R. Pote College of Engineering and Management, Amravati. Here, I am delivering a presentation on Raman spectroscopy for cancer diagnosis. This is the abstract of my paper. Early cancer diagnosis is very difficult by conventional diagnostic method. Most of the biological molecules are Raman scatterers, and hence Raman spectra can capture a fingerprint of specific molecular species and can therefore be potentially used for biomedical applications. In the present work, we have discussed the difference between Raman and fluorescence spectra. We have reviewed the literature and analyzed the normal and cancerous samples by recording their Raman spectra. Conventional method of cancer diagnosis. Biopsy is the conventional method of cancer diagnosis. Biopsy is the removal of tissue from any part of the body to examine it for disease. Complications that arise from biopsy may include bleeding, infection, accidental injuries to adjacent tissues or organs. Also, precancer such as dysplasia and carcinoma in situ, which are only 0.2 to 1 mm thick, are very difficult to detect by biopsy. So, in order to remove these drawbacks, new techniques for cancer diagnosis can be developed. Tissue autofluorescence spectroscopy can be successfully used to diagnose early cancer. But it has some drawbacks as the spectral features are broad and show less specific difference between normal and cancerous tissue. Most of the biological molecules are Raman scatterers. Raman spectra exhibits sharp spectral features and thus provides more information about a given tissue. Here, diagram showing the fluorescence and Raman scattering. Here, the literature review is given. Several groups have studied the potential of Raman spectroscopy for detection of breast cancer. Raman spectroscopy of various gynecologic tissues were first studied by Alfano et al. Characteristic Raman feature of normal tissues and malignant tumor from the cervix, uterus, endometrium, and ovary were studied. Red et al. Employed Raman spectroscopy to study the malignancy of human breast tissues. Feld and colleagues have done extensive work on using Raman spectroscopy for breast cancer. The experimental arrangement is discussed here. Samples of tissues were collected and their Raman spectra were recorded. This setup consists of diode laser, a transmissive imaging spectrograph with holographic grating. The 785 nanometer laser is coupled to 200 micrometer core diameter fiber. The optic arm of the probe, consisting of collimating lenses, a band pass filter, and a focusing lens, delivers the laser light onto the tissue. The other optic arm of the probe, equipped with collimating and refocusing lenses and a holographic notch plus filter, is used for correcting tissue Raman signals. The holographic notch filter is used to block the Rayleigh scattered excitation laser light while passing the frequency shifted Raman signals. The scattered radiation is detected by the intense radiation of nitrogen-cooled CCD camera, which is controlled by computer. Here the Raman spectrograph for 4 different tissues are shown. Result and discussion. We have recorded the spectra of 4 tissues samples at 6 different positions. The height of the peak displays the degree of malignancy. The curve for normal tissue appears to be at lower intensity. whereas the curve for malignant tissue appears to be at higher intensity. Also, the peak of the curve shifts to a longer wavelength as spectra moves from normal to cancerous cell. For example, the peak at 1425 cm inverse for normal tissue in first sample attributes to collagen. However, in malignant tissue, collagen band was found to shift to 1445 cm inverse. Conclusion: the position, intensity, and shape of peaks in Raman spectra of cancerous tissue were significantly different than those of normal tissues. The detailed study of vibrational levels of biomolecules such as amino acids, structural proteins, and lipids can help in the study of differentiating cancerous cells from normal ones. More number of Raman spectra are to be recorded and investigated so that the degree of malignancy can be studied. Development of Raman instrumentation is also needed to make it reasonable so that it becomes affordable to the people.